Hello, my name is Swetaparna Mohanty. I am a graduate student at UMass Amherst, and my poster presentation at the CSAT 2021 meeting is on the topic of determination of ultra-high strain rate impact hardness of metals by energy dissipation method. I would like to thank my collaborators at University of Connecticut and Northeastern University for their contribution to this work. This research was supported by the US Army Research Lab. The plastic deformation behavior of metals has long been a subject of extensive research. One of the key parameters that are useful for understanding the deformation kinetics in metals is the strain rate sensitivity. Studying microscopic hardness of materials under both low strain rate and high strain rate can extend our knowledge of the rate dependent mechanisms contributing to plastic deformation processes and high strain rate strength of metals. Our experimental setup consists of an advanced laser-induced projectile impact test or alpha lipid that can quantify materials characteristics attend from extreme collision events or at ultra-high strain rates. The image A here shows an illustration of the alpha lipid setup. The current research focused on the impact hardnesses of aluminum and copper using alumina of 20 micron diameter as an indenter. Image C shows the acceleration of an alumina indenter and its subsequent rebound from the target after impact. The ultra-high strain rate dynamic hardness was determined as a function of impact energy and volume of impact indentation. The change in kinetic energy was calculated from the velocity profiles of the alumina indenter. From the indentation profiles using laser profilometry, the residual depth of penetration or H max as shown in image D was found, which was used to calculate the volume of impression. These results were then used to calculate the hardness at ultra-high strain rates. These results were then compared with a quasi-statically measured hardness from Professor Siku's Lee group at UConn. For the low strain rate nanoindentation studies, a diamond tip spherical nanoindenter of 20 micron diameter was used as illustrated in figure F. The nanoindentation results gave the force versus depth graph. The area under the loading and unloading curves gives the energy dissipated by plastic deformation, or del E. Furthermore, the experimental results were validated with FEA simulation from Professor Sinan Muftu's group at Northeastern University based on Johnson-Cook plasticity models. The results from all the experiments have been summarized in this slide. Ratio of the energy dissipated by plastic deformation to that of the residual volume of impression gave us the hardness values. From the graph in figure A, we can observe that the impact velocity is higher in case of aluminum, indicating more energy dissipation compared to that of copper. We can see that for both aluminum and copper, the hardness increased with increase in strain rate. There's a steady increase in impact volume with increase in impact velocity for both aluminum and copper, but for a particular impact velocity, the energy dissipated in aluminum is higher than that of copper. This might indicate copper offers higher resistance to plastic deformation than that of aluminum. Low strain rate hardness was determined from the energy dissipation of the load depth profile of a spherical nanoindenter as shown in figure B. We can observe small elastic recovery of both copper and aluminum samples, indicating the major deformation to take place plastically. Also, from the slope we can see that there is less elastic recovery of copper as compared to that of aluminum, indicating aluminum to be a softer material. The low strain rate hardness calculated was 3 times higher for copper than that of aluminum. The FEA simulations were then carried out for the low strain rate and ultra high strain rate indentations to find the material parameters and for its validation. By comparing the plots for aluminum and copper, we can see that the material hardness as a function of energy dissipated is greater for aluminum than that it is for copper when going from low strain rate to high strain rate. Thus, we can conclude from the low strain rate hardness and ultra high strain rate hardness results that hardness is strain rate dependent and aluminum shows greater strain rate sensitivity than that of copper. Thank you.